There's more coming out about it. There are otters that eat them
Otters, yeah.
in certain parts of their range.
Yep.
But nobody else really has this kind of response to it.
Right. So we've been thinking a lot about predator-prey interactions, and we'll continue to think a lot about predator-prey interactions. We're going to touch back on quantitative genetics today. We're going to review some of those things and start to apply those concepts to the newts and snakes in this circumstance. So I wanted to remind us of a few things so that these things are fresh in our minds. And we can see exactly where they fit in to this topic. There are some different types of selection. And the types of selection really reference sort of the directionality of the change. Remember that if we have directional selection, and I'll just orient you to this figure, here we have the phenotypes of some organism and the frequency of which that phenotype is found in the population. Here you can see the shortest individuals make up, let's see, 2.5%, 0.025 frequency in the population. The tallest also make up only that much of the population. The majority of the population here in the beginning has a sort of intermediate height. And if we have directional selection, we want to impose directional selection for tall individuals, what do we need to do to this population? What would you do if you were trying to make super tall giraffes?
Take out the shorter portion so that she does get past the line.
Okay, so you would prevent the shorter individuals then from reproducing to generate the next generation. So we take out those shorter individuals as indicated by this red shade here. What's going to happen to our mean phenotype, which began here? It's going to shift to the right. Okay, and that shift to one direction is directional selection. Now, would it still be directional selection if instead of removing the shorts, we went ahead and removed the tall and selected for short individuals? Would that still be directional selection? Yes, it would just be directional in a different direction, right? If we're to be directional, it has to go in one direction, hence the word directional. And we can see that the frequency then shifts, the frequency of the distribution of the frequencies shifts. We have our mean here, our mean shifts to the right. What else happens to that curve if you were to describe the change in its shape and location? It's narrower, okay. What does that tell you about the resulting population?
Smaller.
Not necessarily, because these are frequencies, right? So it could be made up of only 10 individuals. You would still have a certain percentage in each case. So it probably is smaller from when we take those individuals out. If we actually removed them from the population, it would be smaller briefly. But that's not necessarily what's reflected in the change of shape. That shape is narrower. What does that tell you?
More individuals have the same frequency than they did before, so that there's less of a spread.
There's less of a spread, there's less variation. And if this trait is genetically determined, which it has to be in order to have responded to selection, then we have less genetic variation now that we've removed some of it, right? Okay, so we start out with a lot of genetic variation, and then we get selection operating, and that may take some of that variation out. Okay. For stabilizing selection, if I wanted to impose stabilizing selection on this population, what would I do? Think back or think about what the word stabilizing might indicate. Kylie, what do you think? What would you do to impose stabilizing selection here? You would want more in the middle range? Okay, sure. And so what would you do to the parental generation? Okay, and so nobody that has an extreme phenotype then would be allowed to reproduce. Sometimes this is called balancing selection. Okay, so we're getting rid of those guys. Here's how our distribution will change. Is our mean phenotype different? No, it's the same, but we have less variation and we're more centered right around that phenotype. Okay, disruptive selection. You guys know a really excellent example of disruptive selection that we've studied in class so far, right? The finches. What kind of disruptive selection were they undergoing in the 1960s, let's say, at Academy Bay? Landry, what do you think? What kind of disruptive selection were the finches undergoing in the 1960s in Academy Bay? What was going on?
It's like leading towards the extremes of the beak length, so small and large, like intermediate.
Okay, no intermediate. And if we were doing artificial selection, we could just take out the intermediate individuals and not allow them to reproduce. How is this happening in the wild, though? There was no one out there being like, hey, you're too intermediate. I'm going to prevent you from reproducing.
They didn't push out because they had this circle.
That's after the 1960s, when disruptive selection was gone.
They were being limited by the types of seeds.
They were being limited by the types of seeds. If you had an intermediate beak, you probably weren't really great at eating small seeds, and you probably weren't really great at eating big seeds. And so those individuals that were really great at one or the other were doing better than you were having more offspring, right? So in that case, this intermediate phenotypes are being removed. And lo and behold, here's what happens to our distribution. We've gone from a unimodal, one lump distribution to what? Bimodal distribution. Bi meaning two distributions, right? Where we have the one of the lower frequencies there in the middle phenotype. Okay, you guys got this, right? You're like experts on types of selection. Do you remember what happens if we don't have as much additive variation for one of these types of selection? What happens if we don't have as much genetic variation? Let's say these guys just didn't exist. Would we get this same shift? Pardon? It's a good guess, but no, won't shift the other way. Because we're going to remove the shortest, but also we don't have anybody that's tall, super tall, in the first place. Might have more average in the next generation, yeah. It can't respond as extremely, can it? No, you're not going to get as extreme heights in the next generation. So how would you change this in order to reflect this circumstance where these phenotypes don't exist in the original population? How would you change this shift in distribution.
The mean wouldn't be as high.
Pardon?
The mean wouldn't be as high.
The mean phenotype would not be as high. So you might have a shift, you'll have a response to selection because it still has some genetic variation, still genetically based. You're still selecting out many of the shortest individuals, but your response is not going to be as large. Your response to selection is not going to be as large. So no extreme tall alleles means you can't respond as dramatically. Not at first, anyway. Over time, you could get some random mutation that would allow you to grow super, super tall, right? So over many generations, you might have the emergence of that genetic variation, because what's the source of all genetic variation? Mutation. Mutation is the source of all genetic variation. So you could have some new mutation come in and allow you to be really tall. So then you could respond dramatically, but really you can't respond very dramatically right away because you just don't have the ability, right? Just don't have the ability. All right, this leads us to Fisher's fundamental theorem. I know this was a little confusing to a lot of you. So basically, it's just a restatement of what we just said. The greater the genetic variation in a trait, the faster and more effectively the trait can respond to selection. If we used artificial selection to select for a third arm for everyone in this class, what kind of response would we get? Exactly. We don't have any genetic variation for number of arms in this classroom. Not right now. We might if we had someone with a mutation, a developmental mutation. Okay. But we all, in this classroom anyway, have 2 arms. We don't have any genetic variation for number of arms. If we selected on number of arms, we would get nowhere. That's an extreme example of having no genetic variation. But really, the more genetic variation you have, the more flexible you are to random changes in your environment. And your ability to respond is greater.
Rose?
Yeah.
As you use the word "your," you might want to remember that we're talking about a population, not an individual.
That is an excellent point. So when we talk about responding to natural selection, individuals have their own performance, and they have their own, in that they have their own fitness. But individuals aren't really responding to natural selection themselves, as far as the evolution of a critter. So whereas natural selection operates on an individual, the evolution, the response to that natural selection happens on a population-wide level, right? So the response itself is a change in the frequency of alleles in a population. In fact, that's the definition of evolution. Evolution is a change in allele frequencies over time. So whereas natural selection or artificial selection can operate on the individual, and it does operate on the individual, it operates on your individual fitness, evolution itself is measured as a change in allele frequencies. All right, so Fisher's fundamental theorem says that the greater the genetic variation for a trait, and we should specify genetic variation exists on a population-wide level, yeah? You have your own genotype, but you don't have multiple genotypes for that particular gene. The greater the genetic variation in a population for a trait, the faster and more effectively the trait will respond to selection. So the faster and more effectively the population, the trait will change in that population. So regardless of what Fisher's fundamental theorem says, it refers to amounts of genetic variation. So remember how we measure genetic variation, right? Heritability. What makes something heritable? How does a trait have to qualify as heritable? If I'm going to say a trait is heritable, what does that mean? Okay. That's certainly true in both biologically heritable and non-biologically heritable things, right? So if you have an inheritance from your family, that's also passed down from generation to generation. If you have family lore and legends, that could be passed down from generation to generation. So what do we need to add to this to make our definition biology and genetics specific? Okay, it's a trait, all right? On a genetic basis. Now, when we talk about heritability, oh, do you have a question?
Oh, I wanted to.
Oh, you're going to add, okay.
Yeah, there has to be variation in said,
There has to be variation.
so human heads aren't heritable.
Genetic variation for the trait must be present. Okay. We're interested in things that can change over time. We're interested in how they can change and how fast they will change. If you have something like number of human heads, that's not very interesting. It's essentially the heritability of that is 0, right? Because everybody gets a head. So yes, it's passed down from generation to generation, but everybody gets it. There's no variation in it, or very little as to be negligible. Now, just as a reminder, note that heritability is indicated by h squared, but it's not actually a square number. Heritability is heritability. It's unfortunate but true that it looks like it's squared. Don't square it. Don't take the square root to get the heritability value. H squared is heritability. All right, and this is what you just said. In order for a trait to be heritable, it must have a genetic basis. There must be genetic variation, basically more than one allele for the trait, and it must be passed down from generation to generation. And it can be calculated. Do you guys remember how we calculate it? We gave an example of how we actually calculated heritability of height for students in this class in 2014, maybe?
I don't remember.
Some
years ago.
Some years ago, somewhere around that time. What did we do to figure out how heritable that trait was? Asa?
Make assumptions and use a formula.
Say it again.
We make some assumptions.
We make some assumptions and use a formula. Okay, how do we do that though? Like if I just collect, what kind of data would I collect, for example, from you guys if we were going to do this with you guys? I'd obviously have to collect your height, yeah? Okay, who else's height would I need to collect? The parents, right? Because heritability is also a measure of how similar you look to your parent relative to everyone else. Okay. There is an equation, so Ace is right. There are several equations. Heritability is just a ratio of additive genetic variation to phenotypic genetic variation. So obviously height is not entirely genetically determined. It also is dependent upon your nutrition, for example. So there are other things that go into this variation in phenotype. The environment, right? And so this VA you can think of as genetic, and this VP is total variation. So heritability also is the fraction of variability in that trait that is genetically determined. Now that's a sloppy definition because there are some non-additive genetic effects, but I'm not going to ask you too much about that. So there are a few ways to think about heritability, right? The ratio of variation in the trait that is genetic versus total phenotypic variation. How similar you look to your parents relative to how similar you look to everybody else. A simple way of calculating it is the parent-offspring regression, right? Okay, so you take the average height of the biological parents, and you plot it on one axis, and you take the average height of all the offspring from each parent couple, and you plot them on the other axis. And when you do that, you can plot a line through all of those points, a best fit line, and we get a slope. And that slope tells us our heritability, right? If the parents and the offspring were identical heights, what would the slope of this line be? Not 0, because 0 would be like flat, right? 1. Right? It would be a 1-to-1 relationship. Okay, mid-parent value, average of the phenotypes of the two biological parents. These are the E&E data. They're the mean of all the offspring heights. So in addition to taking your heights, I would have to take the heights of your siblings, biological siblings, if you have them. Here's the mid-parent height. The gray line is what would just be a slope of 1 if everybody was identical to their parents. And that dark blue dotted line is the actual regression line, and its slope is equal to the heritability of the trait. So slope of a straight line, y equals mx plus b, right?
You mentioned the mean of all offspring heights. That would be assuming that all offspring are in the same developmental stage as their parents, more or less. Because I know my brother is really littleish, but that's because he's younger.
Yes, and so you would have to take the height as like an early adulthood height. So for example, if your parents are getting older enough that they have shrunk, they will probably know what their height was before they started getting, say, osteoporosis. And your siblings would also have to be adults.
Yeah, and when we gathered these data, we excluded children who had not finished growing. And so in some cases, those aren't family means for offspring, it's just
The
college
student.
students. In
Yeah.
other cases, if the student was the youngest person in their family, it included all siblings. So it's a sloppy example, but it's real data from actual students. So.
It's certainly a fair estimation, and when you gather these data in the field, it's much the same way. You're going to have data points you can include and those you cannot. But that's a really good thing to think about, because when you're taking data like these, you do want to think about age and stage, different other things that could impact it. You want to measure take all of your measurements in the same circumstance if possible. All right, so we've got our slope is the 0.92 there, which is pretty close to 1, which is kind of fun.
Isn't that higher than normal? for
It is.
height? I
Yeah.
think of height getting more down in the 0.7s generally in the literature.
Yeah.
So, and that could have everything to do with how the data were collected, and only one child per family in some cases decided.
Right. You're going to get some variation around that estimate. Okay, so here again we have this exercise where I'm feeling super unethical and biased against short people. So I go back in time, and if the parents have a below average mid-parent height value, I don't allow them to breed. So I've marked out everybody with an X here. Okay, so I took out these parents, so they're not parents anymore. Obviously there aren't any offspring coming from them. Okay, so here's my population. Okay. And then selection that I imposed has moved the mean over 2.41 inches. Okay, so that's the force of my selection. I'm going to force the mean to be 2.41 inches taller for the parents. Okay, and then we're going to get some sort of response in mean height from the offspring. So that response is how the mean offspring height has changed, right? So what equation am I leading you guys to? You know this, right? I'm being unethical and I'm reading means. It's the, no, not Hardy-Weinberg. Breeder's equation. Breeder's equation. Excellent. Okay, and so we can use the Breeder's equation to predict responses to selection using heritability, right? As long as we know our heritability and our strength of selection, we can predict the response. We can also calculate the heritability if we know the strength of selection and the response to selection. So that's pretty fun. You can go at this equation in any direction. Okay, so here's back to our example. Our slope here is our heritability, and it's 0.92, right? So heritability is 0.92. And our force of selection is reported in the units in which it exists, 2.41 inches. What's the response to my selection? What should the response be? Calculate it right now. What response do we expect? Pardon? 2.22. Maybe I calculated it wrong. I don't have a phone because mine died.
It's 2.22.
2.22? Okay. So then we get our response. 2.22. And the response is also in those same units, right? So we predict that our offspring in this following generation will be 2.22 inches taller. Mm-hmm.
Use heritability. The first one you wrote. This is the heritability, okay? There must be genetic variation of natural. Written the genetic variation of genetic variation. The ratio of
It's genotypic to phenotypic. So genetic to total. So 0.2 means almost all of the almost all the variation is genetic. Yeah, so for all estimates of heritability, they'll be between 0 and 1. Okay, so it's going to be that. Okay. And I did the math wrong apparently, because I got 2.21.
It's a rounding error.
Oh, okay.
You have in your equation 0.92 and you have in this 0.9165, which is actually the
Math. It's useful.
So, VA is the genetic variation, and VP is the variation in the actually expressed traits. So, why is it the slope where the children are on the y-axis and the parents are on the x-axis? Wouldn't it be the other way around?
Yeah.
The parents represent the genetic variation and the offspring represent the...
Do the offspring not have genetic variation in their phenotype?
Right. And why is it one over the other? In that case, how does that relate to?
These are two different ways of calculating it. They are not necessarily equal. They're two ways of getting the same thing. So when you're plotting parent and offspring phenotypes, you're plotting VP. You're not plotting any VA at all, except that it's included within VP. And so it's not that rise, this isn't rise, and that's not run. You know what I'm saying?
Right.
Is that what you were asking, Asa?
Yeah, I was telling you.
Sorry. Yeah, no, those are two totally separate ways of calculating it. Go ahead.
Just briefly talk to them about how you can measure variance using breeding design and analyzing with ANOVA. They're familiar with ANOVA because the way you're showing them on the board is just a partitioning of variance method.
Sure.
Or will that take too much time?
I have to think about that. So do you mean like in a half-sieve design or a dial-L or something?
Well, I'm thinking of the simplest sort of crossing you would have, which would be a full sieve design, which I realize is a different estimate of heritability.
Yeah.
But if you basically look at variation among families.
I see what you're
versus-
asking for. Yep. Yeah, that is a good way of.
Yeah, I didn't want you to go all the way down that rabbit hole, but just
Right.
start with simple stuff.
Right. Okay. So the other way that you can look at this is,
And it would be useful for them to maybe review ANOVA since almost all groups have an ANOVA table in their lab report.
right, and pretty much everything you do with heritability, you're going to use an ANOVA. Okay, so the other way that you can calculate this is that you can take the means of families. How can I indicate this? Because I didn't think of doing this, forgive me if I have to erase something. Let's say that you plot the distributions of phenotypes within families. Okay, so this is family 1. This is family 2. Okay, so this is frequency, and this is phenotype, and this is large, and that's small, and that's 1, and that's 0. Okay, so if you were to plot the frequencies of phenotypes within different families, and you can do this very easily with model organisms. It's much harder to do with non-model systems, but let's say we've got 4 families here. guy's the swirly family, and this guy's the square family. So this is where I grew up. Okay, so we've got here 4 different distributions representing different families, and they're not always going to be as nicely partitioned as this. They're not always going to have as much variation as each other, etc. But this is an example. In this case, we can calculate within and among variance, right? We've got a mean for each family. And if we calculate variance within family, if you had to say, let's see, whether differences between you and your siblings were more genetic or more sort of environmental. I'm doing a terrible job of this. These families usually that we use are all genetically identical. So that's why it's really different, is that these families all have the same genotypes at every single locus. So in reality, I was going to try to make it more accessible to thinking about it as humans, but in reality, each of these families is the exact, everybody is a twin, basically. It's like 200 twins. I don't know what you would call that.
An inbred line.
It's an inbred line. Isogenic line, inbred line. So everybody's inbred, okay? So really you've got a mean here, and then any variation that you see, is it due to genetic variation within a family or phenotypic variation within a family? Environmental variation, pardon me. Environmental. Everybody has the same genotype. There's literally 0 genetic variation within this family because everybody is identical. Okay? So this variance within is your estimate of environmental variance. And it just so happens that phenotypic variance can be partitioned into genetic and environmental variation. Okay? So if this is your environmental variation, what's your genetic variation? Yeah, variance among. Okay, so you're looking at variation among these groups. That's going to be your genetic variation. So you can also use analysis of variance and inbred lines to calculate heritability. Questions? All right, so if we use the breeder's equation with my 2.41 inches of selection, then the response to selection that's in the same units as the force of selection, and we can say, okay, well, how reliable would our prediction have been? The response of those offspring was 2.203 inches if we were to go back in time and do that twice. So it's pretty close to what we actually see. Mm-hmm.
Does the breeder's equation cater for environmental variation?
Does it account for environmental variation? It does, because, well, in some ways, yes, because it includes environmental variation in BP for heritability. So heritability is genetic variation over phenotypic variation. Phenotypic variation can be broken down into environmental variation and genetic variation. So yes, it's just super embedded within that breeder's equation. Through heritability. Let's say you have something that does have a genetic component, but it's very, 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 very sensitive to environment. And so this environmental portion is really large. and thus the variation in phenotype is very large, you may not even be able to see the genetic effects that actually are there because the environmental effects are so huge. Okay?
It's the equivalent of making all of those distributions really broad.
Mhm.
On the board, and then that masks the effect of family.
Right. So well-fed and attempting to reproduce as much as possible, I might produce 6 offspring, right? And then well-fed, maybe Dr. Klawinski, if he really wanted to have loads of offspring, could have 20, okay? And then in that case, well-fed, we'll say our genetics maybe determine that, okay? But if neither of us is getting very much food, how many offspring we have is not going to be as genetically determined in the same way, right? Because we're having huge environmental effects.
What's the difference between VA and VG?
VA is a subset of VG, and VG has some icky, heinous other genetic effects in it, including dominance, maternal effects, and epistasis. And we will study them in genetics in 3 semesters.
So
Yeah.
if you include the environmental variation into the equation, you get 1 plus the ratio, which is greater than, which is not within the range 0 and 1.
The environmental variation is a subset of VP. Okay, so, and this is always going to be smaller. So VP equals VG plus VE. So the VA is a portion of VG. VA plus V epistasis plus V maternal effects. Sorry, it gets really hairy. You'll have to trust me a little bit on that one. VA is always going to be smaller than VP because it's a subset of VP. If I realized you guys were going to be this interested in the math, I would have prepared to talk about the math more.
An example of other kinds of variation, other than additive genetic variation, is dominance variation, which are the kinds of things that you're used to studying about in genetics, where you have these traits that are either or. You either have a widow's peak or you don't have a widow's peak. You can either roll your tongue or you can't roll your tongue. That's not additive genetic variation, that's dominance genetic variation. We treat those traits differently when we're mathematically not based.
It means that when you have a single allele,
It has a large effect.
yes. All right, so I want us to think about fitness landscapes here. Okay, so this is distribution of a trait that is not a fitness landscape, right? Not a fitness landscape, just distribution of phenotype and frequency of individuals. So now we talked about heritability, we've used it in selection, we calculated our response to selection. Now we're going to talk about fitness. In particular, we're going to focus on traits that affect fitness and are heritable. I might just move this up for a little bit. Now, how do I draw a fitness landscape? You guys had to do this on your exam, right? What do I put on my axes? What's on the y-axis? Is it frequency, like that one? It's some measurement of fitness. So it could be survivability. It could be sort of a overall fitness measure. What else could we use as our measure of fitness besides survivability? What are the components of your evolutionary fitness? You have to survive, but that's not enough. You have to reproduce, right? So you have to have some component of fitness over here. Okay. And on the x-axis, you have phenotype. All right, so let's think of this situation. So in Trinidad, there are some guppies, and they live in a stream, and when they are, the larger they are, the more offspring they can have. What is that called? Dr. Klinsky? When the size of an organism determines how many offspring it can have, isn't there a name for that in ecology? Or am I making that up? I might be making that up.
There is, I don't.
Okay, I'm making that up.
It's just generally true.
Right. In a lot of organisms, and some not so much, but in a lot of organisms, the larger you are, the more offspring you can have. Okay? So,
Although not always, because there are also been allocation decisions that we made. You have the choice of producing a lot of small offspring or fewer big offspring, so we don't have a general name for it because
complicated.
it's complicated, yeah.
Right. Okay. So let's say you're one of these guppies, right? And you want to be big, right? And you want to get big fast because you want to start having offspring first, right? Because you want the next generation to be filled entirely of your own offspring. So given this circumstance, I want you to draw a fitness landscape. Plot fitness against size. For these fish. I'm going to show them the 3
Okay.
next time.
I figured you would, but it's fun to see.
No, that's awesome. I didn't realize. I had done a search for what I was looking for, and I saw those images, but I didn't see that they were dynamic. Okay, what's this? Fitness has nothing to do with your crazy face. Your face is not normally crazy. All right. Okay, we've got some fitness landscapes. What do you describe to me what you've drawn?
It increases as you get bigger.
Increases as you get bigger by some function, right?
A leftward skewed distribution.
Yes. Okay. And so we might have something like that. Okay. And then, when you get really, really big, you start to have sort of weird physiological issues, but we'll just kind of do that. Okay. All right. Yeah, I think that's good. However, the problem is that once you get big as a guppy, there are predators who will eat you now. They can find you easily, and you look delicious. And when you're littler than that, they can't find you very well, and you're not worth their time. And they're going to eat something else that's bigger than you. Okay, so let's do a second fitness landscape. I'm going to get a different color here. And I'm going to specify that this was reproductive output. In our second fitness landscape, our fitness measure is going to be survival. Okay, so I want you to draw that second fitness landscape. What do you think that'll look like? respect to predation. It does not. Just survival. That's why I leave this one specific to reproductive and that one's survival. Asa? Yeah. Yeah, absolutely. And so we might have something that looks quite opposite. It's going to decrease by some function, depending upon how noticeable you are and how delicious you look to the predator. Okay, but this is the same fish, right? So, but we just said that a big fish should have high fitness because of high reproductive output. And so you want to be big, right? So selection maybe would push you in that direction of getting big fast. But we just said that if you're big, you're going to be really noticeable and get eaten. And so selection on survival is going to push you in the other direction. Can that be? Are either of these fitness landscapes true then? Question? Comment?
There seems to be a few scenarios in combining these two selective pressures. Like if one is significantly stronger than the other, like the benefits of being large much outweigh the risks of being eaten, then we'd still have a directional selection towards largeness, or vice versa, the case would be the other way around. But also there would be there could also be like a disruptive selection, sort of like with the finches, where like small ones benefit because they're really small and will be eaten, and large ones benefit because they're able to reproduce a lot before they're eaten. Or we can just have a stabilizing selection because they sort of balance each other out.
Okay. How would you create a fitness landscape that incorporated both of these things? I want you to take a minute, work on it, think about it by yourself for a minute, and then I want you to work with a partner. How would you create a fitness landscape that would incorporate both survival and reproductive output for these fish?
While you do that, I'm going to start pinning back your exams. Do the thing Dr. Reynolds asked you about, but don't fixate on your exam.
We definitely have to have
Sam.
side feeding, and so you have to think of a way to incorporate both survival and
It's a food.
so either you're going to put a physical access like really hard, or you have to add some access, right?
You know, say, the best.
Oh,
You're going to do a Z. You need to do one over on the right. Okay, and then what would it look like? How would that change?
The benefits of reproducing a lot from the pigs doesn't
Okay, so on here, if you come up here to
Austin McIntyre, right? No. National.
Oh, God.
I think that that we're a kid. Wouldn't you just start with the long
Next time, what we'll be focusing on is how fitness landscapes look when you are trying to consider more than one trait. What happens to predicting response to selection when you're looking at more than one trait? We'll look at a special case of that called a trade-off, in which you can either be one thing or the other, but never both at the same time. So for this example, you can either avoid predators or have loads of offspring, but not both extremes at once, right? This is an example of a fitness trade-off. There are a lot of ways that you can have a genetic basis for a fitness trade-off. Those are the ones that are interesting, the ones that have a genetic basis. Your homework for next time is to come up with your best way of indicating both of these fitness landscapes on one figure, so that you could tell me what is if you were this fish, what would be your highest fitness option? What would be your strategy? How big should you get? Okay, so I want a single fitness landscape that incorporates reproductive output, survival, and size. You are welcome to work together, but you'll hand in things individually. So I want the figure itself and an explanation. Question? Fitness trade-off is where you can have high fitness through one measure of fitness or through a different measure of fitness, but not both, right? Like I can live a long time or I can produce loads of babies, but not both. I could be really big and strong, or I can fit into tiny spaces, but not both, right?
So, what if it's totally wrong?
If you're totally wrong, that is okay. What I want is a good faith effort. Think about it. Think a little deeply, okay?
And when you think of landscapes, think of maps. So whenever you think of landscape, you can think of maps. Am I giving too much away?
You can, yeah, don't go too far past that, but okay, yeah.
Yes. You're trying to build a map where the contours of the map are fitness.
Right, and if you were one of these fish, you could swim to a place on the map that would give you a particular fitness level. Yeah? Sound good?
Landscape is a metaphor, but then the visual representation of it
is
like
literally a landscape. Yeah. Okay, that is what I have for today. Come back tomorrow prepared to think about fitness and fitness landscapes.
Or Wednesday.
Not tomorrow, Wednesday. Come back Wednesday. I will be sending out those grade updates for those of you who requested them today.
Can I request it?
Yes, send me an email.
Jack, I'm bringing the thing first.